Welcome surfers, it is Joel and this is Rustlers Atom 2.7. In today's video we talk about reborrowing. Before we start, if you haven't subscribed to this channel yet, this is the perfect time to do it to support the Rustlers project. Let's start taking a look to very simple piece of code. I can create a function that modify a value. We can call the function modify. The function modify the x value that is mutable I32, an integer. Okay, inside this function we simply get the content of x, so we dereferencing x, and we adding 1. Perfect, very simple function. Now inside the main, let's create a mutable data variable that contain 10, an integer value, and we can create a reference to this data. The reference r equal to mutable data. Okay, and now I can simply call the modify function on r, and I can print the content of r. Perfect. This code compile. Yes, compile. We have 11. But if I write again a call to the modify function, modify again, the question is, this code compile? We know that in Rust, a mutable reference like this one in the signature of modify function is not a copy. It handles ownership in a strictly way. So technically, if you pass a non-copy value to a function, it moves. Ownership in this case must be transferred. So the variable r should be dead after the first call of the modify function. But let's try to compile this code. As you can see, this code works. But why? There is a secret trick inside this code. It's called the implicit reborrowing. When you use a mutable reference, Rust doesn't actually move the original reference. Instead, it implicitly inserts a reborrow. Think of it as the compiler secretly writes something like this. Modify mute r, something like this. This creates a kind of temporary reference that borrow from the original r. While this temporary reference is alive inside the first call of modify function, the original r, this one, is frozen. It's like suspended. Once the first modify return, the temporary reference dies and r wake up, so is ready to be used again in the second call of the modify function. This allows us to sequentially use a mutable reference without losing the ownership of this reference. No, this practice, the reborrowing, solves the problem of sequential access. But what happens when we try to do two things at once? Let's do an example of this. I can create a mutable vector. Okay, with the vec macro. 1, 2, and 3. This is the content of this vector. Now I can try to push something inside this array, and I try to push a number that is the length of the array, v.len. Okay, and I can print vector v in this way. Again, this code work or don't work? Strictly speaking, at a first look, this code looks illegal because this function push require a mutable borrow of v, and this function length require an immutable borrow of v. These arguments are evaluated before the function call, so we are technically trying to read the length with an immutable borrow while preparing to push with a mutable borrow. But this code can compile. Let's try again cargo run. Perfect. As you can see, this code compile and the code work well. Why? Because we have another trick in Rust, the two-phase borrowing. So the compiler splits the mutable borrow into two different phases. First, the reservation phase. When we write v.push, the compiler simply notes, okay, we need to mutate v, but not yet, we need to. So in this way, in the first phase, the compiler creates a reservation. Second, the activation phase. In this phase, the compiler evaluates the argument that in this case is v.len, and since the mutation of the first phase hasn't started yet, reading the length in this specific case is safe. Once that's done, the mutable borrow fully activates, looking out everything else, and the push function happens. This special mechanism, the two-phase borrowing, make more instinctive, more intuitive the coding in Rust. For this video, it's all. See you in the next atom. Don't forget to like, don't forget to subscribe to this channel, and don't forget to keep your thinking cap on.